Hello. Today we'll be going over problem 724 in the text. It's a power wheel simulation example of the power system presented in figure 714, data for problem number 7.12. With the exception that we're going to be performing a fault at bus 2 on the particular circuit of interest. So let's navigate to that problem. So in 712, you're provided with data for 3 generators, 3 transformers, 3 transmission lines configured in the order shown in figure 7.14. All the parameters are provided on various MVA bases. The problem is to be solved on a 1000 MVA base. You'll notice that each of the generators has their own particular bases or data, the per unit data on their own particular bases and voltages, with the exception of generators 3 and generators transformer T3. All right, so we'll get to Power World and walk through this example. I'll build the circuit from scratch, show you where potential tricks and pitfalls are in order for you to get the circuit model. So the first thing we're going to do is create a new case. Before we even start drawing, however, it's an important distinction that this MVA base that's required is 1000 MVA base. So here we're going to have to change the MVA base of the system. So we'll change that to 1000. Okay, and now all my calculations for per unit impedances when I did my conversions from generator or transformer or line data onto 1000 MVA base will be consistent with Power World. And we'll go through some particular specific instructions on how to make sure everything's represented on the same base. So we'll start off by modeling the 500 kV bus. We want it represented straight up and down. Size 5, we might make that 3, just to, I know what sizes show up on the one line, so I'll just show you how you can edit those. So bus number 2, also 500 kV, the up orientation, consistent sides. Add in bus number 3, 500 kV as well, the up orientation. We're going to add in the 3rd bus, but we're going to change, 4th bus rather, but we're going to change the orientation to flat, so either right or left. Put the bus size back at 5. So it's also 500 kV. So those are buses 1, 2, 3, and 4. We're going to connect these buses via lines with the impedances that we calculated in the problem. Just to make it easy, we will bring up the solution for the particular assignment. So we know, we run through the calculations, generator 1, generator 2, generator 3, transformer 1, transformer 2, and transformer 3. And each line, there are 3 lines represented, so each line will have an impedance of 0.2 per unit. All right, so that's the data we're going to enter into Power World. Now, keep in mind that we've represented the 500 kV bus, 500, 500, 500, buses 1, 2, 3, and 4. I will also go in and represent buses on the low side of each of the transformers. So our first one was, I believe, 13.8 kV. I also want that in the up orientation. So that will be represented as bus number 5. We'll go back to the solutions here. Actually, we'll go back to the problem statement. So generator number 2 is a 18 kV bus. Generator 3 is a 20 kV bus. So here's generator 2. The low side is 18 kV. And generator 3, the low side is going to be 20 kV. All right, so that will be important when we get to the modeling aspect. So I want to add in a bus. Down here, it will be 18 kV. I want to add a right orientation. Okay. And my final bus is a 20 kV bus. Up orientation. Make sure it's consistent with how it's drawn in the one line that we were given. Okay. Now we want to draw the transmission lines, each with a per unit impedance of 0.2. so we can check nominal line voltages from and to our 500 kV. Hit OK. We've got our first one drawn. Now these pie diagrams are coming out with a really obnoxious size in my model. We can always change that. Drawing our next transmission line from bus 2 to bus 3. And that's a 0.2. Okay. Again, change the size of just the pie display. I'll make this bus a little larger since the orientation is a little different. Add my transmission line from bus 2 to bus 4. Again, 0.2 per unit, 500 to 500. I know my voltages are okay. All right, space this thing out just a little. All right, just so you can see where everything's represented here. All right, now I want to go add in my transformers. So I'm going to add this device in as a transformer. Impedance was, so it's a 13.8 to 500. The series reactance that we calculated was 0.24, I believe. We'll come back and check those and verify them later on. Okay, I want to make that just a little bigger. Okay. Second transformer. That one was 0.133, I believe. We can come back and verify that. And my final transformer, this one I'm pretty sure was a 0.1 per unit impedance. So 0.1. All right. Again, just because I'm a little particular about the sizing of the devices, I'll represent them so that I can actually see that it's a transformer. There we go. It's too small. I'm selecting the pie chart. Here we go. That's the actual transformer itself. Change it to about a size 3. This one I'm also going to change back to size 3. I think 5 looks a little too big for what I'm used to representing here. All right, now we go add in the generators. On the display information, size 5 is about okay. I want this oriented to the left. I do want to make sure I enter the per unit value, so the per unit positive sequence value. So we didn't really calculate a zero sequence. Here's the trick when representing generators. The default in Power World was 100 MVA. We calculated data on 1,000 MVA, so we want to make sure we enter that on a consistent basis. All right, so I've got my generator 1 represented. I'm going to represent my generator 2, facing down, fault parameters. So this one was a 0.24. Make sure I enter the 0.24. Okay. Got generator number 2, and the other one was already given to us on 1,000 MVA base. So we'll go in, and we will say fault parameters, positive sequence impedance, 0.17 per unit. Hit OK. I didn't change the orientation of that one. Go back in, make sure it's oriented to the right so it's out of the way when we're looking at the model. Change the location of these data points to be right near that generator. All right, so it's looking pretty good. All right, notice that I went in and I did not verify the generator MVA bases on these. So I want to make sure I go back and I do that. Okay, now we're ready to run our fault analysis. So Power World, move the location of that bus there on me. All right, so I won't be too worried about that for now. Okay, now we wanted to go to run mode and run our fault analysis. So I right click on bus 1, hit fault, it takes me to the fault display. I want to run a fault at bus number 1. It gives me the faulted buses out of service. Why did that happen? I didn't go in and select any of these buses, the generator buses, to be a slack bus. So I want to go back in edit mode, select one bus as my system slack. Okay. Now I come back to, now I first have to go to run mode, come back to the fault analysis dialog, and I should be able to select bus 1. I want to run a 3-phase balance fault because I didn't define any transformer configurations or negative or zero sequence data, so really the only fault type I'm looking for in this example is a 3-phase balance. I hit calculate, and sure enough, I get values that are within the ballpark of what I expect. Now, we were provided in the solution that the fault happens when pre-fault voltage is 5% above nominal. So we're operating at 525 on a 500 kV base. So if we just hit that scale current by, the scaled magnitude will turn out to be the value if I was operating at 5% above nominal. So sure enough, I get 3.932. My hand calculated values said I should have gotten about 3.933 up per unit. If I want to see what that is in kiloamperes, I can change the units, see what that is in kA. So in amps, 4,540. That agrees with my 4,540. If I want to know what the contributions were from generator 1, from line 2, from different sources, I simply look at my lines, the branches, so I can see that from bus 1 to bus 2, I've got 2,519, almost 2,520 amps flowing. And from generator 1, which was bus 5, I have about, so because it's at the low voltage, it's 65,000 amps over here. You see 1,800 amps on the high side of the transformer. I look at my solutions. How does that compare? About a little more than 1,800 amps, and then 2,600 amps from line to itself. All right, and these values only work out that way because we calculated this with a pre-fault voltage of 1.0. If I actually wanted to go in and change my pre-fault voltage, I can go into the flat IEC 909, change pre-fault voltage, rerun my fault, and now it will give me, to change the bus that the fault ran at there. All right, so I'm assuming pre-fault voltage is now 1.05, which I changed in the options section. So here we see current magnitudes in per unit match up exactly, in amperes match up exactly, and what I expect to see from each of the lines. So from 2 to 1, or from 2 to 1, I expect to see about 2,000 or 2.2 per unit, 2.29 per unit, sorry. And from generator 5, I expect to see about 1.64 per unit, right? All consistent with the values provided here. Okay. All right. Thank you for watching. Oh, well, not just yet. Now for problem 724, which is where we started. We wanted to rerun that analysis with a fault at bus number 2. Okay, so let's rerun that analysis for fault at bus number 2. I see voltage. I set voltage magnitude, pre-fault voltage magnitude at 1.05. So the values I get here are what I expect to see: 5.316, and the contributions from each of the lines. So 5 to 1 would be the contribution from the generator, and 1 to 2 would be the contribution from the line. If I look at the solutions, I expect to see 1.25 per unit. So fault bus at voltage at bus 2, generator supplying 1.25 per unit. And my generator on the other bus providing 1.75 per unit. I can go to look at the bus records, see what the voltages are. So voltage at bus 1 I expect to be 0.25. At bus 2 I expect to be 0. That's the faulted bus. And at bus 3, which is the other 500 kV bus, so this looks like it may be swapped around here. See the different voltage magnitudes for each of the different faults there, right? And they look like they match up pretty closely. All right, that's it. Thank you for watching.